there we go. We've got 80 slides to get through, so it'll go quickly, don't worry. Well, I don't know actually, because I've not tried it. I haven't had time to run through it. So we'll see how that goes. Let me share my screen. Cool. You should see a colorful screen of things and not my notes also. If that's not the case, then shout. Yeah. All right. Is everyone ready?
Yep.
Okay. Right. All right. So this is the deep dive into uploading to NFT.Storage, past, present, and future. One potential future, perhaps not entirely 100% yet, but we're hopefully getting there. If the slides would work, that would be great. Here we go. Okay, so what are we going to do? We're going to talk about some basics, what the environment looks like, basically what the dotStorage APIs run in. And once we've got the basics covered, we will dive straight into how uploading works. So specifically like the data formats the API accepts, and we'll dive into what even DAGs are, what even cars are, and then we'll expand on why sending DAGs is a really good idea. And at the same time, we'll identify some issues with our current requirements for uploading DAGs. And then finally, we'll talk about a little bit of future tech, streaming, because I do that because it's not 100% streaming, but you'll see. And so that will hopefully address some of the problems that I identified earlier in the presentation. So let's get on with it. Let's talk about the environment. Let's go. Environment. If you don't know we use Cloudflare yet, then I don't know what you've been looking at, but we use Cloudflare quite extensively for its DNS, its CDN, but also rate limiting tools and stuff like that, but mostly because it has these things called workers. And if you are familiar with like AWS Lambdas, then you'll feel right at home. It's sort of similar. But anyway, let's delve into that a little bit more. We have some users across the globe. They are users of NFT.Storage. And what they do is they make requests to our API at api.nft.storage. And what Cloudflare does is it spins up workers to deal with those requests. And it does this in a data center that is close to the user. So hooray for that. That's cool. And the more users that make requests, the more workers that are spun up to handle them. And Cloudflare basically does this all for us transparently. We don't have to worry about that. It just happens. We just send them the worker code and they run it. So rad. But what are these worker things? What are they anyway? Well, it's JavaScript. It runs on Google's V8 engine. And yes, it's JavaScript running on the server, which may or may not surprise you. Probably not, actually, considering the audience. But anyway, it's the same engine that you find in Chrome, in Brave, in Opera, in Edge, and also Node.js. But the actual runtime environment is not like Node.js in any way. It's much more akin to a service worker and like the ones that you find in browsers. And that's kind of why they're called workers, because similarity there. And so you'll find familiar APIs in the global scope as you'd find in the browser. So it's like fetch, like form data, like readable stream, stuff like that, that you may be used to if you've ever done any browser development. So there you go. So let's talk a little bit about worker limits. This is really not delving very deep into this, but just going to go into it very lightly because it comes up quite often. So these are just the kind of limits that are really interesting to us. There are others. There's a whole page on the Cloudflare worker docs. We are on the unbounded usage model, which means that we have certain bounds that we have to apply to. But anyway, so different models have different kind of limits to them. They all have a 128 meg RAM limit, I believe. And there is also a 100 meg max request body size. So every request you make to them, the maximum body size it can have is 100 meg. And actually, that's not really the max. You can actually increase it to like 500 meg or more, I think. But considering so what we do is we buffer the data into memory, and we've got 128 meg RAM limit. We can't really increase that to any more because it's effectively we'd run out of memory. so if we were streaming that sort of thing, then maybe we could get around that. But anyway, to us, 100 meg max request body size. Even if we did have like 500 meg, we'd still have people who wanted to upload things that are 500 bigger than 500 megabytes. So anyway. So that's real quick limits, and that is basically environment in super whistle stop tour. Hopefully that wasn't too boring, or I know you guys probably all know a lot of that already. But anyway, so moving on, how uploading works. So how does it work? So what we're going to do here in this presentation is we're going to focus on APIs that are responsible for getting data into IPFS and Filecoin by sending the data directly to NFT.Storage. So that excludes like the other APIs. So like I'm not talking about like the status checking APIs or like the pinning service APIs that we have. It's just the ones that you send data to, and that's kind of the scope of this presentation. It also does not cover anything that happens after we receive the files, basically. So nothing about like how stuff gets into IPFS cluster nodes, nothing about how DAG cargo works and stuff gets into Filecoin. That's just not part of this, just so we're all on the same page. Right, so how does uploading work? Well, first of all, what can we actually upload? First up is files. We can upload files. So you can send files directly to NFT.Storage. You can also send a multi-part request to send multiple files if you like, and they'll get put in a directory for you. And so what NFT.Storage worker does is it takes those files and it builds a DAG, what we like to call a DAG. But wait, what is a DAG? Whoa, okay, deeper, let's go. DAG is graph. Each node is data plus links, and links are just like CIDs to other nodes in the graph. So the CID of any given node is the CID of that node's data plus its links. So you need to know the CID of the links in order to get the CID of the node, the CID of a node, basically. It stands for directed acyclic graph. So there's no cycles. It's not like a rule or convention. It's literally not possible due to the way that it's constructed, and we'll see in just a second. So if we take a closer look at this particular DAG, which is completely contrived, by the way, so don't take it too literally, but this is like the root node, and it doesn't have any data per se, but it does have two links to two other nodes. And what I've done is I've separated out data and links here, but the links are usually part of the data in a node. But this is just for to kind of illustrate it. So the CID for this node is the CID of the data and of its links. So we can't generate the CID for the root node until we know the CIDs for the two children that it links to. So if we look at this node, it's very similar. But what you can see is that we can't generate the CID for this node until we generate the CID for the child nodes it links to. So we eventually get all the way to a leaf node, which does have data, but it doesn't have any links. So that's cool. The data is actually a chunk of the file or files that we're building this DAG from. And we can generate the CID for this node since it has no children. So there's no other like nodes that we need to figure out the CID for before. And so you can see how like a DAG is actually generated from the bottom up from up to the root. Like I said, it's a completely contrived example. So let's have a look at a real life thinger. Let's share this whole thing. This is actually on dag.ipfs.io, but someone updated IPFS in it and broke it. So I fixed it today. There's a pull request, but it hasn't been deployed yet. Anyway, in theory, this tool allows you to kind of visualize a DAG, and you can play around with the different types of some of the options that you get when you import stuff. Like if you use IPFS, then you don't really see any of these options. Some of them are exposed, like you can specify v1 CID and raw leaves. If you specify v1 CID in IPFS and don't specify raw leaves, then it will automatically set it to be true. So that's a gotcha. Anyway, but you can just drag files on here and it will generate you the DAG that you see, and you can see like that each node here has a CID. You can see the number of bytes and what type of node it is. These are all because I specified v1, so this is like v0. Because I specified raw leaves, these are, because they're not DAGPB nodes, they have to have a v1 CID. But anyway, the rest should have v0 CIDs. Anyway, this is what it really looks like, and then you can specify, like you can mess around with stuff like that and see the different types of graphs. In MFS, it uses the trickle DAG, and it looks a bit more like this, which is kind of fun. It's optimized for streaming. Essentially, it's not good for seeking, but it's good for like, because essentially like almost every traversal leads you to some data, and it's just good for streaming data out. Whereas with a balanced DAG, if I want to get to this, like this is the first bit of data, I have to traverse like a few intermediate nodes. Anyway, that's just fun. Fun information for you. Let's see if I can share. Here we go. Let's go back to the presentation. Okay. Okay. Again, hopefully you don't see my notes. You just see the presentation. All right, rad. So that's what is a DAG. Anyway, where were we? Okay, all right. So back up. What can be uploaded? So basically, if you upload your files to NFT.Storage, what it does is it creates the DAG for you, and then it puts that into IPFS, into IPFS cluster and Filecoin for you. And we're not really going to discuss that bit, but that's what happens. Okay, cool. And oh yeah, right. So finally, what it does after it's created that DAG and put it in Filecoin and IPFS or IPFS, whatever, it sends you back a CID. So it will give you the CID of the root node of the DAG that it created for you. And so what users have to do is they have to trust that NFT.Storage is doing the right thing and not giving them the CID of some like malware or virus. They actually have to trust that NFT.Storage is doing good and not bad for them. But as we know, it is good. So anyway, it's not trustless, is what I'm trying to say. So let's take a look at the pros and cons of uploading files directly to NFT.Storage. So what we've got, it's really simple. You can just curl, you can use curl your files up, no problem, and it will give you back a CID. You actually don't need a client library. If that wasn't obvious, you can use any programming language that has like a standard library that will allow you to make HTTP requests, which is basically any language, any programming language. Yeah, super easy, basic kind of API. Bad things is, as I just alluded to, it's not trustless. We have to trust that NFT.Storage is doing the right thing. The Cloudflare per request 100 meg limit applies. You can only upload up to 100 megs of stuff. And you can't do things like upload to NFT.Storage and mint your NFT at the same time, because you have to wait for the upload to finish to get that CID that you're going to put in your contract. So you can't do both at the same time, which might be desirable for some people. But anyway, it's mostly the trustless thing. Cool, so what can be uploaded? That's that. What else can be uploaded? You can upload a DAG directly to NFT.Storage. And so, well, actually this also starts with files, and you need a client library that will build the DAG for you. And that client library also needs to be able to serialize that DAG into a car. And this is just allows it to be transmitted. But anyway, what is a car? Oh, yeah, I did change. Okay, great. So wait, what is a car? Let's just deep dive on cars. Typically, once you've created a DAG, it's stored in like a key value store. The keys are CIDs and the values are the block data. And that can be like any key value store, like it could be LevelDB, it could be like a Redis, it could be in-memory map. You can even use Postgres, and we have. But anyway, if we want to send a DAG, we need to kind of package it up so it can be transmitted, received, and then extracted into a key value store on the other side. So we need to create a car somehow. And so this is the format of a car. This is what a serialized DAG looks like in car format. It has like a header section and a data area. And the data is just the blocks of the DAG along with their CIDs. The variants here just describe how long, how many bytes that they have a variant before everything, just to know, so you know how many bytes to read for decoding. Variant is variable length integers, and they're just numbers. Anyway, not important. So the ordering of the blocks in this data area is kind of undefined. There's nothing in the spec that says that you have to order them in any particular way. There is an idea of like a canonical ordering. So you could have like a car that is in canonical ordering format where it's like the blocks are in order of like depth first traversal in the graph. But that doesn't really matter because there's nothing to say that they have to be like that. And we're also under no obligation to include all the blocks for a given DAG either. Like we don't even have to include the block that's identified as the root block in the header. So the header, yeah, like I said, let's have a look at the, oh, cool. Let's try again.
I think technically you don't have to have a root in the header by the spec because it was written a long time ago. But if you don't do that, then it might break in Filecoin. So just, and if you do more than one root, it might break.
Also not good.
So we just like only ever do one root.
yeah, basically. Yeah, right. So the header. So this is the header. It basically tells us which of the blocks is the root of this DAG. Here comes Irakli. Let's let him in. Which of the blocks is the root of this DAG? It supports multiple CIDs, like Michael said, but in practice, all known implementations reading cars expect just one. So the header also has a version number for future proofing, which is not used in car v2 spec, which is fun times. So you can go and take a look at that, those specs on the IPLD.io website if you're really interested in that. But anyway, car v1. Cool. Okay, so back to this. Once we've got our car, or created our car, then that can be sent to NFT.Storage. It accepts car files and it puts that in Filecoin and IPFS. So that's cool. So one thing to note here is that there's nothing to send back here. In the previous version, when we were just uploading files, we sent back a CID, but it's not really, because the client has created this DAG, it already knows the root CID before everything's been uploaded, because it's created the DAG. So we no longer have to trust NFT.Storage is doing the right thing and creating a DAG and giving us back the right CID, because we've created it ourselves. So that's very, very Web3. Cool. So let's have a look at the pros and cons of uploading DAGs to NFT.Storage. Limitless. The amount of data we can actually send is unbounded. The 100 megabyte limit effectively doesn't exist. And we will go into more detail on why that is in just a few moments. The same thing for resumable. We actually don't have to start from the beginning. If an upload fails, we can start from a previous section. And it's also parallelizable. So we can actually send different parts of our files at the same time. And all of those three things we're about to discuss in more detail. So don't worry too much about that just now. The concurrent mint and upload thing that I talked about is now possible because on the client, we're getting the CID of everything. And like before we've uploaded it, so we can now use that CID and put it in a contract and do it at the same time as uploading something that's really big. So that's kind of cool. I'm not convinced that's a great thing to do because you don't know that the thing has got there before you've minted it. But anyway, just saying that's possible. So the bad bits about this is that client-side DAG creation it's a complex thing. You kind of need the library to do it. Not all programming libraries, languages have a library to do this already. Like we've got JavaScript, Go, Rust, some of Python. Maybe?
I don't think we have Rust actually. We just had a thread about this, and Volker was trying to figure this out, and like all of the work to do really easy encoding and decoding of UnixFS working with car files was done in the last year in Go and JS, and so there's no Rust.
Okay, yeah, exactly. So that there's also slight. Well, I mean, I think it's probably not really a concern anymore. But obviously, you have to bundle more code in your application to get this stuff done. So I don't know, it's always a consideration for web app developers. Cool. Okay, so a little bit of history. When NFT.Storage was first created, it was just files. They didn't last for very long. We then added like car uploading, and we also support files at the moment. And but in the glorious future, we will hopefully just support DAGs, but I don't know when that might be. Anyway. Cool. So, like I said, the thing that I'm going to expand upon, we will do that now. So how is sending DAGs limitless, resumable, and parallelizable? Okay, so it's limitless because you can actually build DAGs of arbitrary size and can be as big as you like, and like in exactly the same way that files can be as big as you like, or as many as you like, bounded only by, I guess, your available disk space. DAGs can have exactly the same thing happen. So we'll talk a bit more about that available disk space problem, but make a mental note that when we create a DAG, it's effectively a copy of the data that it represents. So we need to kind of store that somewhere, like either in memory or on disk. Just hold that thought for a second. But secondly, on limitless, sending DAGs is limitless because we actually send multiple requests to Cloudflare. Like, remember the rule that you don't need to include all blocks for a DAG in a given car file. That's exactly what we do. That actually allows us to get around that 100 meg limit by sending multiple car files with different parts of the DAG in them. So that's that. So back to our DAG. What our client library actually does is to create these multiple cars is it packs subgraphs into multiple cars, right? So instead of one big car containing the whole DAG, you actually get like multiple cars for subgraphs of the DAG. And there are a few ways or strategies that you can use to split a DAG. And this particular one I'm just kind of showing here is called tree walk. So one thing to note here is that each car has the same root CID. So Carbytes actually operates on car files. So this is kind of what actually happens on the, you've got the original car file on the left, and it splits it into 3 separate cars. They all have the same root, but they have different blocks inside them. Okay, so and that's basically how it works. To make multiple cars, send them. So let's take a look at the pros and cons of splitting with the tree walk strategy. Cool. So big ones. Having all blocks linked from the root makes the blocks in the car garbage collection resistant. So, and this is something we were thinking about a long time ago when this first came about, and it's not super relevant now. But it's because the root CID is pinned by IPFS. And when you garbage collect in IPFS, any blocks that aren't like directly pinned or indirectly pinned because they're part of that DAG will be collected. So if we happen to garbage collect while someone was in the middle of uploading and they weren't using the tree walk strategy, then we could collect blocks that shouldn't be collected essentially. And this allows us for that to not happen. But in practice, we never garbage collect on our IPFS nodes because it would take forever, and so we just let them fill up. And if we ever want to move stuff out of them, it's better to create like a new node and copy the bits that we want rather than do the garbage collection thing because it's intensive. So secondly, like all cars having the same root CID is the kind of the key to us knowing the association between requests. If we're sending lots of car files, how do we know like which car files are for which DAG? Like they're kind of, is this set for this DAG? Is this set for that DAG? And the only reason we know that they are all associated together is because every single one of these car files has the same root CID. They're the same DAG or part of the DAG. Anyway. And it also means that that we don't create a new row in our upload table for every partial DAG that gets uploaded. Like if we had a big piece of data, we split it into lots of car files and we send up loads, all of them. If they all have different root CIDs, then we get a different row for every root CID. And because they have the same one, we don't create a new row, and your file listing, you have one CID, even though you've sent multiple requests to populate that DAG. Okay, good. So bad bits. We need to understand the data, in that we need to walk the tree, and to do that, we need to decode the blocks and extract the links to the other nodes in the tree. It means that we need to have the relevant codecs for doing that. Like largely it's kind of DAG-PB and CBOR and RAW, but there's nothing to say that other people can like be encoding data with other codecs, and we currently don't support that, and people can't put data that's like DAG Jose encoded, for instance, into NFT.Storage. Not sure why you would, but it just means that people who are building applications that rely on linked data IPLD can't do so right now. So that sucks, and we kind of want to enable that. It's also a little bit slower than other strategies or some other strategies, because we have to do this decoding of all of the blocks and walking a tree, and that whole process is a little bit complex. So there we go. Anyway, so the history of this is we've always used tree walk, because that's what we came up with and that's what we did. And in the future, we would like to, well, what you'll see is that it'll be more like there's a simple strategy. So when Carbytes was first created, there was multiple strategies, and one of them was tree walk. But there's like the simple one is like, just take a car file, keep reading blocks until you've reached a certain amount of blocks, and then send that. And that's like without having to decode the blocks, you just read the car file, and that's the simple strategy. But actually, what we want is kind of we'll see later is like streaming, and we won't need to split, because we'll be streaming the blocks, and we can do that thing without a library to do it for us, essentially. So hopefully nothing in the future, or way more simple than we have, and it will enable these extra use cases and things. Okay, so it's resumable. A DAG is just the blocks that are linked together by CIDs. So it doesn't actually matter what order the blocks arrive in to our IPFS node. It also doesn't matter if we send the same set of blocks twice. So if we've got our like our separate requests, and one fails, then we can resend that. Like the blocks just go in the block store, they're addressed by CID. If we send that same bunch of blocks, you're just going to overwrite stuff that's already there, but the value is always going to be the same. It's not like a regular database where you have like a ID and some changing data. It's always going to be whatever key is, the value is always going to be the same. So it doesn't matter if we fail on one of these requests, we can resend it again. It's parallelizable. Doesn't matter what order the blocks actually arrive in. We have multiple chunks of the graph, multiple car files, and we can just send those requests concurrently. We don't need to send them in parallel, because they actually, like, it doesn't matter the order that in which they arrive. They don't need to be written to disk sequentially in any way. They just need to go into the key value store with key values. So, right. And so, by the way, this is just one file of like 22 meg. It would typically be split up into like a 3 car files, and the end one obviously has less, because that's the end of the file. Didn't quite reach 10 meg. All right, and so we get to the future tech bit, the streaming bit, which is not quite streaming. I'm introducing. Trying to think of a better name for this, and I came up with JIT car. It's kind of like Uber for cars. Anyway, so it's not quite streaming. We have this magical black box that Irakli is working on. It's like the streaming DAG builder, and you give it files, and it spits out blocks as they are created, and we accumulate the blocks until we reach a certain threshold. So, so like block, 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 block. And then so when we have like 10 meg of blocks, like we send that car to NFT.Storage, and then we start again. Block, 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 send that off. So we're still buffering into memory a little bit, but after every successful request, we can reclaim whatever memory we were buffering into, and it would effectively allow us to transmit like DAGs of completely arbitrary size, bigger than our memory, bigger than our disk, and we wouldn't have to store the entire DAG beforehand in memory or on disk. So remember when I said that make a mental note of what do we do with this DAG that gets created that's a copy of the data? Well, we throw it away after we sent it, essentially, because we're streaming it out. So we're kind of winning, right? Yeah, but not so much, because there's this problem. So you might have noticed these question marks in our car that we're creating. This is the header of the car that I've got here in this slice. And this is where the root CID goes. And so earlier we learned that a DAG is created from the bottom up. So we actually don't know what that root CID is until we finish creating the DAG. So, what goes there? Okay, so you might have seen or heard the word session kind of banded around in conversations we've had, and like a session for what we're talking about is like what associates multiple car files together. So right now the session is the root CID in the car, but what can we do in this new world of streaming? So what ideas we had? So this is kind of a combination of like things that people have been saying, but also like ideas that I've been trying to put together. These are just a few ideas I just wanted to talk you through, and they're not like set in stone, but this is like, we could do this. So let's just have a look. So first of all, what you could do is you could just not have a root CID. Like there's a thing called the empty CID, and it's a valid CID, and it looks like this. Let's get this thing out of the way. So the problem with use it, so yeah, it's like it's an identity CID, like there's no block associated with it, but it is a valid CID, and you can use it. So the thing about using this is that unless we make some sort of special provision in the API, you'd actually get an upload registered against the CID in your files list, and like we could fix that pretty easily, I guess. The bigger issue is that like there's nothing to tie these uploaded cars from one upload session to the next. Like I don't know like if these cars belong to this DAG or that DAG or whatever, because I'm just sending cars with like an empty CID as the root. And there's another problem here where like we actually store cars that get uploaded in S3, and so what we'd end up is like a directory on S3 that is like BAF K Q AAA with like hundreds and hundreds of cars in it, and we didn't know like what cars belong to what DAGs or anything. Like we'd have no way of knowing at all. So that kind of sucks. I think we could probably figure something out there. But anyway, the second idea was like use an IPNS key. I've talked previously about like IPNS in Web3.Storage, and the keys that it creates look like this, and they're actually also CIDs, because you can put them in cid.ipfs.io and it'll tell you all about it. So what would happen here is that a client would generate a key, and then when it's finished uploading all of the, it would use this key, this CID as the root for all of the cars that it uploads, and when it gets to the final one, it would update that name, that IPNS key, to the root of the DAG, because on the last one it actually knows what the root is, so it can update a name to point to the root of the CID and then send that. And then on the server, we'd check, like when we receive each car, we'd check to see if the root CID, like that name key got updated to point at a CID yet. And when it does, then we're kind of done. So that's kind of fun. There's like a variation on that, which is like the IPNS key gets updated to point to a block in the last car that gets sent, and that's like a manifest which has like the sort of root CID in it. So but also like maybe it has a list of cars that were uploaded that make up the DAG. So it's kind of fun. it does rely on like the client updating an IPNS record, and that like extra API request that needs to happen to somewhere else or a different like route is like, it's a little bit racy, and it doesn't, it's a bit hacky. I'm not super comfortable with it. And also,
did you see a Rockley suggestion about that though? So a Rockley suggestion is to actually take that IPNS record update and put it in the upload request, like in the headers. So when you upload the car file that has the data, it would also have the IPNS record update. And so it would all happen in one transaction rather than being 2 calls.
Yeah, that's cool.
Yeah.
So yeah,
you're
cool.
absolutely right. It's very racy. It's very, very racy without that. You're absolutely right.
Yeah, exactly. But anyway, so there's a third kind of idea I had, which kind of doesn't really rely on IPNS at all. But in this one, like, we'd actually send empty CIDs, but the final car would have a CID that is actually a CID pointing to a block in that final car, which is this manifest. And then like when we receive, and the manifest lists out the cars that were uploaded. So any cleanup we have to do on the server, like when we get that final car and that block, we could look at that manifest and be like, okay, well, I've put these things in S3 under the empty CID. Now I can move them into the right place, so that you could do that. There's also no reliance on IPNS. So, and it would also mean that there's no real like breaking change to the HTTP API, like the old style kind of true cars can still work. But we don't have this additional kind of way of uploading cars where the final car has this manifest in it, which tells it what was uploaded already. So that's kind of fun also, and no IPNS. So all of these things, like the one thing that that they would allow us to do is like not add a row to the upload table until we receive that final car and we know that we've got all of the data, which is rad, because at the moment we have a real problem where we, basically the first car we get adds a row to the table, and people are like, when uploads do fail, they're like, well, it says that it's there, but it's queued or pinning or whatever, and people were like, oh yeah, but it also did fail, and now I don't understand, and so that would be a really good UX win. If we did this this last one, I was totally spitballing here, we could have like the manifest could look like this, where it's literally just the route, the hashes of the cars that you sent, which would be fun, and so that would be great. So I'm aware that Oracle has submitted a pull request for another alternative, but I've been working on this basically all day and haven't read it, so I can't comment too much on it. But that is my presentation. Thank you very much for listening. Hopefully it was enlightening in some way.
Super helpful.
Yeah, really cool to hear that.
Yeah, so it's really interesting. I think I have not considered using the IPNS key as a CID to like in the car files, which is somewhat interesting. What I've been thinking is slight variation, I think, on that, where we could have a special block definition that basically says update this IPNS key. And there are 2 types of updates. One is amend. So all the blocks that are included in a card are just made part of the new set. And another variant is a transaction saying, and now change that to that other thing. Does it make sense? So, so in a way, you encode blocks that represent transactions, and they tell you what to do. An idea is that in the roots, you list out the transaction CIDs, and then you kind of interpret those.
Let's schedule a call maybe tomorrow morning if we can get it, or early next week, just for the 3 of us to just go over all of these potentials and just kind of discuss them, see if we can get to a resolution, and give the next 3 minutes to any other questions about like the rest of the talk, because I think that this won't resolve in 3 minutes. So.
Yeah. I'd say mostly this talk is about like getting everyone to the same level where we all know what the current problem is and what we're trying to solve, rather than like me explaining individually to everyone like how we've got from here to there and what we currently support or not. And we like I said, the future stuff is kind of a little bit up in the air. We still need to figure it out. We got like 2 minutes for questions if anyone has anything.
My only question is like, is there any like very simple solutions that we can use today that would not require backend changes to be able to associate cars with like some CID? I think your IPNS key might maybe allow that. Like if we just upload a bunch of cars and put an IPNS key in the root CID, I guess that will insert the records in the table, right? That will where the key will be IPNS key.
Yeah. I don't know if that's a good thing. Like that would actually probably like mess up Reba quite considerably.
Like I think that a model in which the car uploads are much more atomic is probably just a bit more scalable. Like my concern is that like in that case that you mentioned where we don't, because we don't have a root, we don't create anything in the database table until the uploads are happening. Well, we're basically creating these incomplete states that we never garbage collect, and that the user just kind of like, we also like have a problem with even displaying that to the user, right? Like we would still have to display the incomplete state in some way because it is being stored. And I don't know if we're actually like accounting for it properly if it's incomplete.
So short-term hockey solution could be like, we just display the last root, right? So if there's many records for the same CID,
I think that
we just
using the root. So like look at the large file upload use case for a second, right? You basically like take a big directory from something like Hashlips, and then you've got to upload all the assets and then change all the local JSON files to those asset URLs and then upload those. So you literally like you don't know what that root's going to be, and you're going to basically have to stitch together a directory at the end, right? And that's all one big state that needs to be collected together. It's like, we're not going to have like an automated way of doing that. That's going to have to be client tooling that's created for that specific use case. And like, I'd like to find a model where we have a transaction that you can do where you're updating this IPNS key with some kind of state record, but we don't have an opinion about that state record. And you can do other stuff with the state record, right? So you could do stuff like that. You could do other use cases that like where the whole DAG actually has partiality. So even that final state root is not like complete within those car files, right? Like if you were uploading like the latest updates to the Solana chain, it's going to be probably more than 100 megabytes, but it's also going to be incomplete because it's going to link to the whole history of the chain, right?
By the way, on the somewhat unrelated, but like say IPNS key sync got me thinking, because I didn't realize IPNS keys were valid CIDs. And given that they are, like what happens when you like navigate to the IPFS/IPNS key?
If you go to
gateway just gonna
IPNS key?
No.
Oh, it will redirect. No, I mean if you don't put IPNS, you do IPFS/.
No. The IPNS record is not a valid IPFS because it's not a hash. It's like it's a public key.
But it is CID though. It seems like we have a multi-hash.
When you resolve it,
yeah, it won't work from the gateway because it won't.
Yeah, it resolves to a record that has a hash sometimes.
A record. Wait, what is a hash for? It's a hash over the private public key.
Yeah.
Okay. No, but I think it is interesting. Like in theory, we could do the redirect, right? Because we know we can spot those keys and do the redirect to IPNS, which I think would be a very useful thing to do, given what Michael was telling me the other day, which is like we already have a hard time communicating two protocols, IPFS and IPNS and stuff. But if we can meaningfully do those redirects, I think that would be really.
Yeah, if it's a libp2p key.
Cool.
CID.
Oh, I gotta run.
Okay. Any other quick questions before we leave? All right. Thanks
Let's
for
say
coming
thank
in.
you.
Thank you, Alan.
Thank you for giving this.
Thank you.
Yeah, it was fun
Thanks,
to
Alan.
hear
It's a
this
really
nerd
good
stuff.
presentation.
All right. Thank you. Bye-bye.